Hello student, today we will discuss about the self-inductance under the topic of electromagnetic induction. First we recapitulate the previous knowledge, that is magnetic flux. Magnetic flux through any surface is the number of magnetic line of forces passing normally through that surface. Here we have a surface and the number of line of forces are passing through them. These are magnetic line of forces and they are passing through them. But we consider here the number of line of forces which passes normal to the surface. If we say the magnetic line of force having magnetic field intensity in this direction, then we will consider the normal surface. The normal surface is this one. The direction of ds will be perpendicular. So we will consider the number of line of forces perpendicular to the surface. So the number magnitude will be B cos theta. The component of magnetic field toward the area direction will be B cos theta because it is toward the angle. Eta is showing the direction of area. Eta is showing direction of area. As we know, the magnetic flux is the product of area of the surface and the magnetic field. Phi is equal to B dot A. The magnetic field of induction is B and area is A. So flux is phi is equal to B dot A. And so we can say flux phi is equal to B A cos theta eta. As you know, vector A dot vector B is equal to AB cos theta. So we are saying the number of line of forces is equal to BA cos theta. Now remember here the product is dot product. So the flux will be a scalar quantity. So we should write here flux phi is equal to B dot A or BA cos theta. Here eta is the component of B toward the normal area. So phi is equal to BA cos theta. This is magnetic flux. For a small element area, if we say the area is ds, if this area which is shaded here is very small, then flux will be written as phi is equal to B ds cos theta. Right? Now, the flux may be changed by these four conditions. As we know, flux phi is equal to B A cos theta. So this flux can be changed by changing the area magnetic field, by changing the area, or by changing the angle between magnetic field and the area, that is theta, or any combination of effect. It means you may change together BA, together B theta, together A theta, or all these three. So flux may be changed by these four conditions. As we know, the Faraday law of induction tells us whenever there is a change in magnetic flux, if there is a change in magnetic flux, then there will be a production of induced EMF. If we say, if we have a coil and if there is a change in magnetic flux, then it will be their production of induced EMF. If we have a coil and inside them the magnetic field is regularly changing, it means the flux is changing. If there is a change in flux regularly, then there will be a production of induced EMF, one side plus, one side minus. So the difference between the ends will be the potential difference, and it is called induced EMF. And the second law, which we already know, this the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux, right? And according to Lenz law, we discussed this earlier. According to Lenz law, the production of induced EMF always oppose the cause of change. So that we will write here the negative sign, right? So if we say the magnetic field is changing, the magnetic flux, there is a production of induced EMF, and the induced EMF is negative rate of change of magnetic flux. Now we have an experiment that is called Stephan experiment. Stephen's experiment having a coil with a bulb along with a battery and switch. In this experiment, whenever the switch is on, it means the circuit is closed. The current will start to flow from the battery, and it will be distributed in two sides from the junction. Some current is passing through the bulb, and some of the current is passing through the coil. Because of this current, I2, the bulb will glow. What happened here? The, as we switch on, the current will start from minimum level to maximum level. Minimum level to maximum level, from 0 to maximum value. So the current is through the coil will also change the value from 0 to maximum. That is, in coil it is I1. So current change in coil is 0 to I1. Because of this change in current, there will be a change in magnetic flux. There will be a change in magnetic flux. And if there is change in magnetic flux, there will be a production of induced effect. And the induced EMF will oppose the change of increase of the current. So from Faraday law of induction, change in magnetic flux induced an EMF, and induced current flow in the coil. According to the Lange rule, the direction of induced current is opposed the flow of current. At it oppose the growth of current. So induced EMF is created just opposite to them. Hence there will be induced current. So in red line, I shows induced current, which oppose. So what will happen? As we switch on, the real current I1 goes from 0 to I1, and slightly it will get the induced EMF, and the current will decreases according to this red induced current. So the bulb will glow from dim to stronger length. So bulb will start from dim and will be bright. And in case of second part of the experiment, if we open the switch, the current will start to decrease from I1 to 0. through the coil. Hence, what will happen? The magnetic flux also decreases from maximum value to zero through the coil. And from the Faraday law of electromagnetic induction, the change in magnetic flux will induced as EMF, and induced current will flow in the circuit. Now, as the current is decay, then the induced current will move in opposite direction. It will move opposite direction. So there will be a change in magnetic flux and we will get the induced current according to Faraday law and Lenz law. So there will be an induced current flows through the bulb. The induced current will flow through the bulb even the switch is off. If switch is off, there will be no current from the battery, but induced current will be there for a very small time period because of the closed circuit with coil and the bulb. And bulb will start to get a flux. It means it will reduce from brighter level to zero. Just as we can say, when we release the key of camera, when we are taking the photograph, there will be a flux change and there is a flashlight when we click the key of camera. Now the today's topic is self-induction. Self-induction is a phenomenon of induced EMF in the self coil due to the change in current. Here we are taking a coil of length L and the value of current is I. Area of the coil is A. If there is a change in current, induced current will be developed. The phenomena of induced EMF developed by the coil is called self-induction. The induced EMF oppose the growth or decay of the coil current and hence delay the current to acquire the maximum value or the minimum value. So self-induction is called inertia of electricity. As we know, if any object is in motion, it will remain in motion under until there is no external force. If any object is in rest, it wants to remain in rest until and unless there is external force. That was the inertia of mass. But here we are taking inertia of electricity. So, according to inertia of electricity, it opposes the growth or decay of current. As we know, flux is equal to B dot A, and for a coil, B is equal to mu 0 Ni. So, the flux is directly proportional to current. How? Mu naught is permeability of vacuum. It is constant. N is number of turn per unit length of the coil. It is constant. Area of the coil is constant. So flux is directly proportional to current, or flux is equal to Li. Here L is called the self-inductance or coefficient of self-induction. So self-inductance is denoted by L. If current I is 1 ampere, then L will be equal to phi. The self-inductance is defined as, now we are defining the self-inductance. Self-inductance is defined as magnetic flux linked with a coil. Thus, self-inductance is defined as the magnetic flux linked with a coil when unit current flow through it. As we know from Faraday law of induction, E induced is equal to minus d phi by dt. So E induced is equal to minus L di by dt. We put here the value of flux and plug this value in the equation of Faraday law of induction. Then E induced is equal to minus L di by dt. Di by dt is the rate of change of current. And if di by dt, the rate of change of current is 1, then the self-inductance L will be E induced. The self-inductance will be E induced. The self-inductance is defined as induced EMF set up in the coil through which rate of change of current is unity. If the current changes per second by 1 ampere, then the induced EMF produced in the ends of the coil will be the self-inductance of the coil. The unit of self-inductance is given by Henry. Self-inductance is said to be 1 Henry if 1 ampere current in the coil linked magnetic flux of 1 Weber. Or self-inductance is said to be 1 Henry when unit rate of change of current 1 ampere per second, induced EMF of 1 volt in the coil. Now self-inductance of a solenoid. Magnetic field due to solenoid is, we know, B is equal to mu 0 N I. Here N is number of turn per unit length. If there are number of turn on the coil is N and the length of the coil is L, then number of turn per unit length will be N by L. If we take only a single turn, this one of the coil, then flux per turn is B dot A, that is mu 0 N IA, or mu 0 N IA by L. The flux linked across the end turn of the coil will be mu 0 NIAL into N, because we have to multiply the value of N because there are N turns in the coil. So we will get phi is equal to mu 0 N square I A by L, or phi is equal to Li. Taking the equation phi is equal to Li, we compare it. We compare these two. The L will be equal to mu 0 n square A by L. Or if we take per unit length turnkey form, then it will be mu 0 n square A L. Tomorrow we will discuss the energy in inductor. Thank you for joining the meeting.